With this, we move on to the next invited presentation by Professor M.S. Shriram. Sir is president of Professor K.V. Sarma Research Foundation, Chennai. He did his PhD in physics in 1978, that also happens to be my birth year, from IIT Kanpur. He joined Department of Theoretical Physics, University of Madras, and retired as HOD in 2011. He has worked in the areas of high energy physics and non-linear dynamics. He has engaged in research in Indian astronomy and mathematics over 30 years. He has several papers in this field, and he has co-authored 3 important works on the Kerala School of Astronomy and Mathematics. He has been recently elected as Fellow of the Indian National Science Academy. And the topic for his presentation is Nature of Discourse, Evolution of Ideas, and Systematization in Indian Astronomy. Over to you, sir.
I thank the organizers for inviting me to this conference, but I was a little hesitant to accept because my talk may not have too much to do with cosmological concepts, things like that, and also it will be somewhat technical, so it will not be that attractive. But anyway, he said that no, I think we will, they said that it is covering all aspects of the Indian astronomical tradition, so it is all right, even if it is, somewhat away from cosmological concept. But I would touch upon the cosmological concepts towards the end, at the end. So, first a recollection of the historical development of astronomy in India. So, in the Vedic period, of course, it starts. So, there are many, many references to sun, moon, planets, earth, meteors, etc., and eclipses, as was mentioned in the previous talk also. Now, observation of stars are necessary for performing the rites at the correct time. So, names of many stars are mentioned. The spherical nature of the earth is implicit in many statements in Rig Veda. And there are several references to eclipses. The Svarbhanu, the Asura striking the sun with darkness, it was mentioned during the discussion after the first talk. And they refer to family members of Atri being well versed in understanding eclipses. And nakṣatras, that is somewhat unique to India, though of course it was adopted by China and other places later. So, this is moon's sidereal period, that is for the moon to go around the background of stars. One cycle is close to 27.11 days, that is moon covers nearly 1/27 part of the ecliptic per day. Ecliptic is the path of the sun in the background of stars, and moon's orbit also is close to that. In fact, the orbits of all the planets are also close to the ecliptic. So, it is natural to divide the ecliptic into 27 equal divisions, also called nakṣatras. And each day is associated with a nakṣatra. To this day, this practice, is there. So, now, there are the 3 main time units that are there, in all civilizations. So, day, month, and year. So, these are the 3 clear time markers, as even casual observation of the sky will reveal. So, day is of course the duration between 2 successive sunrises. Month is the time interval between 2 amavasyas or 2 paurnamis. So, that is between 2 successive new moons or 2 successive full moons. So, and year of course is the time for the sun to complete one orbit in the background of stars. Of course, from the geocentric framework, there is nothing wrong in saying that sun is moving around the earth. From the geocentric framework, that is nothing wrong with it. So, and most of the earlier astronomy was geocentric. Okay. And all major civilizations grappled with them and the correlations among them. So, so daily motion of objects is, it's called diurnal motion. So as we see in the left figure, so we see the objects rising in the eastern portion of the sky. It's not east always, eastern portion of the sky. It will go up, okay, and then it will come down. So this is the diurnal path I have drawn in the figure. So that path will be a circular path, and it is, inclined, to the vertical. If Z is the zenith, okay, that and the inclination depends upon the latitude of the place. And so that is what is observed, okay. That is called a diurnal path. And I will come to the declination and all that later. The equator itself, so the circle which is joining the east and west portions in the sky, the great circle. So the distance of this path from equator is called declination. And apart from the diurnal motion, the objects move in the background of stars. The stars themselves, as we see, their relative orientations will be fixed. Whereas sun, moon and planets and all that, they seem to be moving in the background of stars. So if moon is near some Chitra nakṣatra one day, the next day it will be some other nakṣatra. So that is because it moves in the background of stars. And apart from that, of course, daily motion is there. So both are there. Yeah. And year and months, the earliest Vedic texts also refer to year and month. So, for instance, this shloka is in Rigveda, Dvadasharam nahi tajjaraya vavarti chakram paridhyam brutasya aputra agne mitunaso atra saptashatani vimshatischa tastuhu. The wheel of time formed with 12 spokes revolves around the heavens without wearing out. O Agni, Anita, 720 suns. That is refers to days and nights. So, year has 12 months and 360 days. So, this is in the earlier period. Later, of course, the references to, 360 was seen to be quite inaccurate. So, 5 or even 5.25 days added later. And the months or seasons are discussed in Taittiriya Samhita, among some other texts also. Madhu, Madhava, constituting the season, Vasanta, Shukra, Shuchi, constituting Grishma, Nabas, Nabasya, Varsha, Isha, Urja, Sharat, Rutu, Sahas, Sahasra, Sahasya, and Tapas, Tapasya. And concept of Adhikamasa was already there, even in the Vedic time. That is very interesting. Mention of 2 more months than the 12, and they are called Samsarpa and Amhaspati. Perhaps the latter is the Kshayamasa. So this kind of a calendar, even now we practice, though of course the calculations are more accurate, and the names of course now we are calling it by different, Chaitra, Vaishakha, Jyeshta, Ashada and all that. 12 months are there, and Adhika Masas are there. Earlier, the calculations, I will come to that, how they were, these earlier calculations. And then of course now with true positions of sun and moon, it will be more accurate. But the concept is, followed even now. Masas are there and Adhika Masas are there because, you have to align the lunar months and solar year. Yeah. And the northern and southern motion of the sun and equinoxes are also mentioned. For instance, in Taittiriya Samhita, it says that Tasmat Adityaha Shanmaso Dakshine Naiti South Shat Uttarena. That the sun moves southwards for 6 months and northwards for 6 months. And the equinoctial day is mentioned in Aitariya Brahmana. And solstices find mentioned in many places, example Kaushitiki Brahmana and things like that. And it's mentioned that at solstices, sun turns northward and southwards at the 2 points. So what is meant is the following, that as I told you, it is from a geocentric framework. So imagine the earth at the center. So you draw a big circle which is parallel to the equator. Okay. So that is called a celestial equator. the sun is moving in the background of stars around the earth. So this thing is inclined to this equator. So that is called ecliptic or Kranti Vrutta in India. And so this the largest deviation occurs at solstices, the point which is, maximum southern point. So that is the southern solstice or winter solstice, and this. So this concept of ayana was, there in a very long back, even in Taittiriya Samhita. Now, all these things, at least as far as you know, mostly it was qualitative. Year was there, month was there, ayana was there, and all that. But there was no systematic calculation procedure, it appears. So this comes with the text Vedāṅga Jyotiṣa. So, though of course a 5-year yuga cycle is mentioned in Taittiriya and Vajraseni Samhitas, and as we saw, the calendar is there with intercalary months and 27 nakshatras as markers of moon's movement. Now, in Vedāṅga Jyotiṣa, we have a definite quantitative calendrical systems. And it comes in two, this thing, Rigveda and Yajurveda Jyotiṣa, Vedāṅga Jyotiṣa, two recensions as they call it, and is ascribed to sage Lagada. In one of the verses, it says that Swarakramete Somarko Yada Sarkam Savasavo Syat Tadadi Yugam Magaha Tapah Shuklo Ainam Hyaduk. When the sun and moon occupy the same region of the zodiac, together with the asterism of Vasava, that is Shravishta, at that time begins the Yuga, and the synodic month of Magha, the solar month called Tapas, the bright fortnight of Magha, and then goes Uttarayana. So this is the description of a 5-year cycle, in the Vedāṅga Jyotiṣa, and where it begins each cycle. Okay, so winter solstice was beginning of the asterism Shravishta at that time, is identified with Delphini, and this corresponds to some time between 1370 BC and 1150 BC. May it have been written a little later. Of course, this is according to the Indian scholars. Most of the Western scholars, they will say that you can't say which segment of Delphini they say. Is it the beginning of the Delphini, this thing, or some other point? So there may be errors and so on and so forth. They'll place it only at around 500 BC. Okay, but anyway, so this is certainly earlier than 500 BC. So Yuga concept is mentioned, as I told you. The whole calendar is summarized thus. So Trishat Yakhnam Sashat Shashti Rabdaha Shat Charvato Ayane Masa Dvadasha Sauraha Sihu Yetat Panchagunam Yugam Savanendustru Masanam Shashti Saika Dvisaptika Dutrimshas Savanaha Sardaha Suryaha Strunamsa Paryayaha. So 366 days form the solar year. In the year, there are 6 Rutus and 2 Ayanas, that is northward and southward courses of the sun. The 12 solar months, Dvadasha, this thing. 5 years make a Yuga, Panchagunam Yugam. And in a Yuga, there are respectively 61, 62 and 67 Savana months, lunar, synodic months, and moon cycles. Okay. So that is the Savana month contains 30 days. And this plus half, 30 and a half make a solar month. And the 60 is the number of solar months in a Yuga. Okay. So this is the calendar. So it is very clearly mentioned. So here, Vedāṅga Jyotiṣa Yuga consists of 60 solar months, 62 lunar months, and 67 sidereal months. Okay, sidereal month, remember, is moon coming to the same point in the space, okay? Whereas a lunar month is conjunction between sun and moon. So lunar month is nearly 29 and a half days, whereas a sidereal month is 27.11, that kind of. So then we can see that a sidereal year is about 366 days, lunar month is 29.516 days, so actually is slightly less than actual. And sidereal year is slightly more than actual. And lunar month, and sidereal month is 27.301 days. And actually, so it's slightly less than the actual. So 60 solar months are there, and 62 lunar months are there in 5 years. So 2 Adhika Masas would be there. Okay? So probably 3 lunar years are with 12 months, and 2 lunar years with 13 months in a yuga. And tithi as a division of the ecliptic is very clearly, described here. It is 1/30th of a lunar month, and there are 15 tithis in each parva, half of a lunar month. Now, what is important about Vedāṅga Jyotiṣa is in the Sutra format, So, this is perhaps one of the first mathematical astronomy texts in India. Here, mathematical astronomy is basically arithmetical astronomy. Because for any accurate description of astronomical phenomena, you need trigonometry. So, it was not there at that time.
So, just a quick question. Sidereal year actual will be also 366?
No. Actual is that 365.2564. No. Tropical year is 2421. Yeah. The modern sidereal year is 2564. It's slightly more than 25. Here it is too much. Yeah. I will come to that, how we can understand this. And so Sutra format, of course, it is known that in all Indian disciplines, it was some kind of a Sutra format only, you see. Like Pāṇini's Ashtādhyayi is in Sutra format. And Pingala Chandra Sutra is Sutra format. So that is the way Indian mind worked, okay. So you give it in Sutras, so people will, understand it and, quickly remember it. It's easy to remember Sutras and then for any calculation or something they want to do. And explanations are in commentaries. So I will come to that. So the short algorithms for finding tithi, nakṣatra, sun's position in the sky, etc. So it is the first text in India to give mathematical algorithms in astronomy. There is hardly anything on planetary motion in this work. Now, sidereal years of 360 days is too long. I mean, you may think that, it is only slightly 365.2564 and 366. But over the years, it may be, already observations, if you make observations, okay, you will see that sun and moon would not come back to the same point at the same time in 1830 days. There will be quite divergence, which even naked eye observations will reveal. So, sometimes it has been interpreted like T.S. Kuppanna Shastri. He is one of the persons, Kuppanna Shastri and K.V. Sharma, they brought out a edition of Vedāṅga Jyotiṣa. So, his opinion is that it is primarily to provide a civic calendar where convenience of division and ease of calculation is important. Okay? So, by that time they would have realized that some inaccuracy is there. And so some corrections would be introduced to obtain tolerable position to the sun, moon, and so on. So there is probably dropping of 2 intercalary months in 13 yugas. So then 65 sidereal years will be 13 into 62, okay, minus 2 lunar months. So 23,742 days. So that will be closer to a sidereal year. 23,742 divided by 65. I mean, that is what he is opining, and it may be true, because many times in later Indian Siddhāntic texts also, they will always give, approximate value first, Then they say, let us make it more accurate, Sputikaranam, okay. And in fact, it's called bija correction in various texts. So it's possible. So anyway, we need not discuss it further. So there is a definite mathematical astronomy with definitive algorithms in Vedāṅga Jyotiṣa. Now, variation of the daytime over the year, you see. So now, you would have observed that the sunrise to sunset time, you see. So that is always 12 hours or 30 gatikas at equator, but other places it will change. It may be more or less. So that is because of the sun's motion northwards or southwards. So if it is north of the equator, so then this diurnal circle, the daily circle of the sun, more than half will be above the horizon, and the duration of the day will be more than 30 gatikas or 15 muhurtas or 24 hours, 12 hours, okay? It will be more than that. Whereas if it is south of the equator, it will be less than that. So that is the variation of the daytime over the year. Now, very interestingly, this text Vedāṅga Jyotiṣa gives a formula for the duration of the daytime on any day, after the day count, starting with the winter solstice. So this is the So this is the thing, So that is number of days which have elapsed in the northward course of sun or the remaining days in the southward course doubled and divided by 61 plus 12 is the daytime in muhurtas of the day taken. Remember that 30 muhurtas is one day. Okay. So the duration of the given is, the daytime is 12 plus 2n by 61 muhurtas, where n denotes the number of days elapsed after the winter solstice when the sun's course is northward and number of days yet to elapse when it is southward. So on the winter solstices n is 0, so d2 is the duration of days 12 muhurtas. And when it is equinox, it is 91.5, so it is 15 muhurtas, and summer solstice it is 183, that will be 366 by 2, and it will be 18 muhurtas. So this is the formula that is given, simple arithmetical formula. In fact, when you plot this variation of daytime with n, so this is the thing we get. The straight line is what is, got by the Vedāṅga Jyotiṣa formula, and I have plotted this for 27 degrees and 29 degrees. So they are very close to this straight line except at solstices. They are close. Whereas at 35 degrees, it is, quite, the agreement is good only at solstices. And most of the days it is off. So why I am giving this 35 degrees that, so one of these Western astronomers of the yesteryears, Pingree, he said that, the shortest day to longest day ratio is 12:18. So that is happening only in, 35 degrees. So it should have been, perhaps something which was observed in Mesopotamia, which was borrowed into India. But Wahashi, one of the Japanese astronomers who passed away recently, he analyzed it and said that, for if you take a latitude of around 28 degrees, then it is very close to the modern formula. The Vedāṅga Jyotiṣa formula is close to the modern formula, except at the solstices. So it seems that it is depends based on observations at some location with latitude between 27 and 29 degrees. The exact modern formula is stated in later Siddhāntic texts. So like duration of daytime, so a figure is drawn, I don't know, it may not be drawn that nicely, but the main important point is that, so that, so when the sun is in the equator, that when it rises exactly in the east and sets in the west, so then the duration of the day will be the sunrise to sunset 15 muhurtas or 30 gatikas, whereas at some other time, any day, it will be 2 into 15 plus or minus 1/6 delta alpha in gatikas, where delta alpha is called chara. So that is the portion, what is known as 6 o'clock circle, the circle which connects the east, west points and the pole star. That's called the 6 o'clock circle. So when the sun has a northern course, so then the circle will, more than half of it will be above the horizon. So that part which is, extra from 90 degrees, that's called chara. So the chara is this formula, okay? So the expression for chara is given in Indian text from Aryabhatiya onwards. It is given. This is the duration of the daytime. It is given in terms of a formula. See, this is very important. But if because, many scholars, Western scholars say that Indian astronomy, etc., is borrowed completely from the Greek and all that. Where is the formula in Ptolemy? There is no formula for the duration of daytime. It's not that he didn't understand. It is all completely understood, but there are tables after tables for everything, the tables after tables. Whereas here the modern formula are there in, which is given in terms of, sine and cosine functions. And that is because of the way we define the sine and cosine functions. So you can write it in terms of formulas. So that is an important thing, and it is given in this kind of a formula from Aryabhatiya onwards in all the texts.
Before Aryabhata, Pancha Siddhantika
I am coming to that. That also gives that in a way. It does. But it is, Pancha Siddhantika is actually composed around 530. Okay? So he might have borrowed some elements of Aryabhatiya also. It is possible.
but he has faithfully reproduced the
No. Some of them are preferred. It can be ascribed to, this Paitamaha Siddhanta, this, that, and all, Saura Siddhanta, and all that. So it is possible then some Saura Siddhanta also might have this, the older version of Surya Siddhanta, which is not, we don't know, that also may have this kind of a formula. Yes, that is possible. Yeah. But the recorded text which is there, Aryabhatiya, which is, so definitely can be 499 CE. So that has this. So certainly from that time onwards, this is there. That's what I'm saying. So then, the use of gnomon for determining directions. So a prominent feature of the Śulba text, so that will be, adjuncts to Vedas. So is a reference to west-east direction, how to find that. So the fixing of these cardinal directions is one of the features of Śulba geometry, because all these Vedic rituals and Vedic, Vedis, construction of the Vedis, so you should know the exact east-west direction. So that is why, so this was given in the Katyāyana Śulbasūtra, it gives that, but how to find the east-west line. Same Shankum Nikhaya Shanku Sammitaya Rajva Mandalam Parilikya Yatra Lekayoho Shankograchaya Nipatiti Tatra Shanku Nihanti Sa Prachi. So essentially the OX is a gnomon, some stick or some vertical object with a pointed tip. Okay, so then you find out, you also draw a circle around the gnomon, okay, and then you find out when the shadow of the gnomon enters that circle in the morning and in the before noon and afternoon. Okay, so take those points. So then the line passing through those points, that is the east-west line. So having put a gnomon on the level ground and having described a circle with a chord whose length is equal to the gnomon, two pins are placed on each of the 2 points where the tip of the gnomon shadow touches the circle in the afternoon and forenoon and afternoon. The line joining these is the east-west line, Prachi. So if it enters this on E prime and W prime in the forenoon, so because the shadow will be in the reverse direction, right? So if the sun is in the eastern part, the shadow will be in the western part. So W prime in the forenoon and E prime in the afternoon. So then the line joining them, because it's symmetrically it will be there, you see. So this equal shadow is possible because of the equal, it should be symmetrical with respect to the north-south line. So you do that. Now, but there is a slight inaccuracy in this, because the sun's circle itself will change. As this declination circle or the day circle will change. So that is, we will come to that. Pancha Siddhantika also gives essentially the same thing. Okay, so plant a gnomon at the center of a circle, etc. In fact, there is not necessarily, the circle need not have any particular dimension. Okay, it should be a circle that is all of reasonable radius. So then the shadow, equal shadow, where the shadow enters and exits, the same circle, you see. So that is the east and west points. So Pancha Siddhantika also gives the same thing. Now Brahmagupta takes up the method in east-west line. This is the first verse in this Triprashna chapter. Okay, so Triprashna is the 3 problems of Dik, Desha and Kala. Dik, direction; Desha, location; and Kala, of course, is time. So in that he gives this verse: First verse is this. Purva parayor bindu tulya chayagrayoho dig aparadhyaha purva anyaha kranti vashat tan madhyat shankutalam itare. The east and west points correspond to equality in shadows tips. The first one is the west, the other one is the east. And he just says kranti vashat, that is all. There is, so what exactly he means, we'll come to that. There is change due to declination. The ones in the middle line passing through the base of the gnomon are the others, okay, north and south. That's what he says. So he is just indicating that there is some change, correction due to the kranti. And Prutudaka Swami in his commentary, there's a commentary by Prutudaka Swami. So there he discusses this. Purva parayoho kapalayoho bindu karya tulya chayangula agrayoho edi namakranti vashena digbeda upapadyate, etc. Okay, he says this. So mark points at the tips of the equal shadows in eastern and western hemispheres. If at all there is a difference in the direction, it is due to declination. So then he gives, find the or sign of the declination and so on. So how much you should shift that point? You got the point by observation, you have to shift it a little bit, one of the points, to get the exact east point. So he is giving that. Okay. So explanation is quite brief in Prutudaka, here at least. In fact, it is more of a description of the correction rather than explanation. So I have written EZW is that equator. At the equator, the celestial equator is vertical, okay, and the north pole is on the horizon, okay. So now I have written two diagonal circles which are north of this equator. So there will be vertical circles at the equator, okay, and that centers of these diagonal small circles are C1 and C2 are R sin delta. You see, that will be the distance between that and the center of the celestial sphere, O. So OC1 is R sin delta 1, and so declination. So this difference is this. Then, now what is observed is, a stick, a gnomon, okay. So gnomon you are using and then you are measuring the shadows. So you have to relate it to what happens, for a shadow due to a given gnomon, okay. So that has actually a hypotenuse equal to 12 by cos z. Chaya will be, suppose OX is a gnomon, the shadow will be OY, which is 12 sin z by cos z, or 12 tan z, and the chaya karana XY is 12 by cos z. So your celestial sphere had a radius R, and here you have to take a circle with a radius K, 12 by cos z, okay. So then in that circle, so the change will be this, R sin, change in the declination, so krantijya, and into K by R. Then, but it is inclined, actually it is inclined. So for any other location, you have to take into account the inclination. So for that he says that, you have to divide by cos phi. So finally, so this is the change you have to affect when finding the true east point. Of course, this will be very small. In solstices, when sun is in around June 21st or December 21st, it will be very small, okay, negligible, but for any other day, this will be there. And so this is the correction you have to do, and whether you have to shift it northwards or southwards, that is, that depends upon the ayana, okay. So if the sun is moving northwards, you have to shift the observed point to the north. Yeah. So this is the.
As far as we know, Brahmagupta and Vedāṅga are the first to give this correction.
I mean, it's first to describe the correction. Yes, I think. So. No. Aryabhatiya Bhashya doesn't. Aryabhata itself doesn't discuss this determination of directions. At least in Aryabhatiya he doesn't. And I didn't see it in Bhaskara's Aryabhatiya Bhashya. Yeah. So, in Siddhāntic ceremony, of course, Bhaskara gives a more detailed upapatti, He gives a more detailed law of proportionality and all that he uses, and he gives this correction. Okay. Now, relation between the time and shadow. So, I mean, I'm trying to give how it evolved, like, Vedāṅga Jyotiṣa, duration of day, and, then the later text, and east-west determined the direction, and then how it was corrected later, and how it was explained. So, now relation between time and shadow. Time is very important, okay. So, the earliest, even Arthashastra will give the relation between the time, at a what is the corresponding to some given instant, and the shadow of a gnomon again, okay. So, when he says that when the shadow of the gnomon of height 1 Purusha is 8 Purushas, 1/18th part of the day is past. When it is 6 Purushas, 1/14th is past. When 3 Purushas, 1/8th is past, and so on, okay. And when there is no shadow, it is midday. When the day has turned, one should understand the remaining parts in like manner. So, essentially it says that if T by day is a fraction of the daytime, which is elapsed since sunrise. So, since sunrise, suppose this is the fraction of the day, this thing, then the relation to the shadow is d by 2t is s by g plus 1. S is the shadow of a gnomon of height g. A better formula is given in Pancha Siddhāntika. So, he says that multiply the daytime by 6 and divide, for a 12, he specifically mentions a 12 angula gnomon. Okay, in that, the formula essentially what he means is this: d by 2t is s minus s prime by g plus 1, okay, where s prime is the midday shadow. So, he doesn't take it to be 0, so he takes it to be some, whatever the thing. He should put it in the formula. So, this is also approximate, but in the same text later, he will give the exact formula for the time from the shadow. So, time is a very important thing, and it can be determined from the shadow. So, now Brahmasputra Siddhanta is one of the, in fact, Aryabhatiya itself gives the exact relation between time and shadow, you see. So, it gives that, and commentary by Bhaskaravan explain it, but Brahmasputra Siddhanta is more detailed in topics related to this time and shadow and all that. So, I am referring to this, what is given in Brahmasputra Siddhanta. So, what he says is the or sign of the time elapsed or to elapse. From it, the chara is subtracted in the northern hemisphere and added to it in the southern hemisphere. This is multiplied by the radius of the diurnal circle and divided by the radius. And to this, the earth sign is added in the northern hemisphere and subtracted from it in the southern hemisphere. The result is the cheda. The cheda multiplied by or sign of the colatitude and divided by the radius is the shanku. Okay. So, I mean, don't worry about this technical aspect, what they are trying to do and how they are explaining, how they are describing. That is what, I want you to concentrate on. So, this is the, you have to draw this circle, okay, and EW is the east-west line, SRST is the rising setting line, okay. So, now the circle, diurnal circle I have written, okay. So, suppose sun is at some S bar, okay. So, sun is, let us take the time before sunset, ST is the time at which, at the point at which sun is setting. So, S bar, ST, that will correspond to the time. So, time is measured along the equator or the diurnal circle, okay. So, that arc refers to the this thing. So, you just have to degrees. If you do it in degrees, okay, the time will be in degrees, okay. If you divide by 15, okay, it will be in hours, right. So, like that. So, now, so what he is saying is take this, some chara will be there, which is already mentioned, okay. So, that is the extra duration of time due to the when the sun has northern declination. So, he gives this way to do it, Shanku, that is the R cos Z. So, it is given by this formula, okay. This is the formula that is. And one interesting thing is that algorithm itself incorporates the proof. So, he wouldn't have been able to give this formula unless, he knew how to draw these figures and, write it, right. And the algorithm itself, from the algorithm, from the way it is, the various angles, etc. are, incorporated in the formula, Okay, so that is the proof itself. So geometrical proof is there inside the algorithm itself. So if Shanku is, then this is the shadow from time. But if the time is to be known, the Shanku is known. So, and time, which is essentially theta plus chi. Chi is the chara, and theta is that, one portion above the this thing, what's called the unmandala. Okay, unmandala point. So that is the. So essentially, it is 90 degrees minus the hour angle. Hour angle is, is the time after meridian transit. How much time it has taken for an object to come from the meridian transit, that is when it is on the north-south line, north-south circle to a particular point. So that is called the hour angle in the modern astronomy. So this theta is 90 minus that. Okay. So this is the how time can be found. And explicit formula is there from the measurable quantities in Pancha Siddhāntika. So direct formula. Okay, suppose you have this gnomon of length 12, okay, and then the shadow is OY. OX is the 12 angula, the gnomon. OY is the shadow, okay, and the sun is, rays are coming at the angle Z with respect to the vertical, this thing, okay. So then you take that and so how do you find out from this? See, from the shadow. From the shadow, how do you find out that? Okay. So from the shadow, spare the shadow measured in digits, add 144 and get its square root. Multiply this by the square of the co-latitude, etc., etc. Otherwise, divide the result by 6. The result is the time in Nadi after sunrise. Okay. Okay. So this whole, from the shadow itself, one can find out the time, you see. So very clearly, you just have to measure the shadow, okay, and then you have to follow this procedure. So then you will get the time. So that is the, okay. So now, noon shadow is very important. So from the noon shadow of of sun or anything, and from the latitude of a place and declination, the location of sun on the ecliptic, the declination and longitude, they can be found from the noon shadow. You see, declination can be found. The sun's position on the background of stars, the longitude of the sun, so that can be found from the shadow. So this is what is described in Brahmasputa Siddhanta. So at noon, the sum of the sun's declination and latitude or difference when they are in the same direction or opposite directions is the zenith distance in degrees. When they are R sine of the zenith distance multiplied by 12 and divided by R sine of altitude, the result is the noon shadow of the day. The midday shadow is obtained by methods stated earlier. So this gives a clear algorithms for that. So when it is, what I am saying is the sun is on the north-south circle, midday, okay. So midday means that is the sun is on the meridian, the circle which is, connecting the east, west point and the zenith. So that's half circle, halfway circle in the celestial sphere. So when the sun is on that, okay, suppose the shadow is that, OY. So from that you can find out the so-called zenith distance, or the angle, okay. The angle at which the sun rays are coming and hitting the tip of the shadow. And from that angle, if you know the latitude, then you can find out the declination of the sun. And from that, the later text will tell you how to find out the longitude also. Okay. So that is the how it is. Now, latitude can be found. How do you find the latitude? So that is when the declination is 0. So when sun is on the equator, then the noon shadow will give the latitude. But and that also can be we can see when equinoctial. That's called an equinoctial day. So when does it happen? That is, that can happen when the tip of the shadow is a straight line. The tip of the shadow traces a straight line only when on 2 days in a year. September 23 and March 21st. That is when the declination is 0. Okay. So on that day you find out the latitude directly. Okay. But Brahmagupta gives another method. Okay. He gives shadows at 2 different times on the same day. Okay. So that is suppose the K1, B1 are the Chaya Karana, and Chaya Bhuja means the component of the shadow perpendicular to the east-west line. Okay. So they are the, so then this shadow will be, the latitude can be found out from this, So K1, K2, B1, K1, B1, K2, B2 are there. So from that you can find out on any day itself, and this is later described by Bhaskaracharya also in Siddhānta Shiromani. He will describe it in detail. Okay. So now this is a little technical, but I will just mention it to, what I am trying to convey is how it evolved and how, things, there is some remarks by some scholars, that Indian astronomy was static. Okay, and they were, doing some things without actually understanding the full significance. Okay, and there was no much evolution. Okay, so people kept on following, okay, in a very mechanical fashion the earlier text, and they were doing the calculations in that way. This is not at all true. So as an example, I've been giving this. So it's called a Kona Shanku. So that is when the azimuth of the sun, the sun is on the north west or northeast or southwest or southeast directions. Okay, exactly. So when you call, it's at the 45, azimuth is 45 degrees. You see. So because this ZWE, that is the vertical, they are called a prime vertical, then that is north, then you take a line which is 45 degrees from that, circle which is 45 degrees from that, that's called Kona Shanku. So then he will give the formula for the shadow, essentially Maha Shanku or cos Z for this in a kind of a situation. And so this could be not possible. You couldn't have given this formula without solving the quadratic equation in detail and, very carefully drawing the diagrams and all that. So it couldn't have been possible. And he mentions when the declination is larger than some value, then, he gets one other solution is possible. Okay. So normally, if you have a quadratic equation, ax squared plus bx plus c is equal to 0, the solutions are this. This is famous, already high schools. It is taught minus b plus or minus square root of b squared minus 4ac by 2a. So normally only the root with plus sign before square root of b squared minus 4ac was considered in ancient mathematics. Okay. So though the known that 2 roots are there. Because in fact most mathematicians were not comfortable with negative sign before Brahmagupta. You see. So in fact the European mathematicians were not comfortable with negative quantities even till as late as 18th century, 19th century. That's what, I heard some eminent scholars saying. So here he has taken the other root also, and when it is physical root, physical means, that situation should arise when the sun is above the horizon. Okay. So then you find out the shadow and all that, and you can find out from this formula. Now, Bhaskara generalizes this to an arbitrary azimuth and follows in Brahmagupta's footsteps. Essentially, in Brahmagupta's solution, one has to replace half by sin squared a, where a is the azimuth. So then he says that, 2 more solutions are possible. So that is the importance of that. And he, of course, gives it in great detail, describes it in great detail. He says how the solutions, first of all, he has to set up the equation, set up the quadratic equations, and then use this algebraic notation. So, like how we write now, except that the left-hand side, right-hand side, you will have above and below, okay? So, there is a systematic way of writing down equations, how to write down the squares, cubes, and all that. So, he writes that and then describes in detail how to solve this, okay? So, that is the important thing about Bhaskara's. And he also tells that how this new solution is obtained. Now this is later, far more systematization took place, for instance, in the Kerala School of Astronomy and Mathematics, like Nilakanta Somyaji's Tantra Sangraha and its commentary Yukti Bhasha. So they give far more systematic. Everything is more, much more systematic. Already Bhaskara had systematized a whole lot of things, in his Siddhānta Shiromani. Okay, so he had taken all the points made by earlier astronomers into account, made the corrections if they are necessary, and also introduced some new ideas, and also explains every concept. So that is Bhaskara's contribution in his Siddhānta Shiromani. So now this Kerala astronomers go further, okay, and there's little more systematization here. So in fact there are 4 variables associated with the celestial body and celestial sphere. Declination, that is the distance from the equator, and the time passed, okay, that is essentially our angle. So then the azimuth, that is in what direction the sun is there, and the latitude of the location. So these are, including the latitude, there will be 5 quantities. So, and Tantra Sangraha gives the algorithm for finding any 2 of them when 3 are specified. So there are 5C2 or 10 problems. The algorithms are given in Tantra Sangraha in a section called Dasha Prashnaha, and full derivations are given in Yukti Bhasha. Okay. So sometimes some statements are made that proofs are not there, only some brilliant flashes are there. Indian and mathematics and astronomy, there are no proofs. All the proofs are given, for these 10 problems in Yukti Bhasha. And as I told, Bhaskara himself in his Siddhānta Shiromani in 12th century, whatever algorithms is given, he has given the proofs. Okay. So now it is time to wind up the lecture and make some concluding remarks. So Indian astronomy was not static. It is mainly algorithmic. That has been noted by all the scholars as far as the main texts are concerned. But explanations are very much there in the commentaries. We have given some explanations like Prutudaka Swami's explanation for some things and things like that. Yeah. And in the context of planetary motion, there were some advances. In Siddhānta Shiromani, Bhaskara presents a very different method to find the rate of motion of planets, which gives a very satisfactory account of retrograde motion. So retrograde motion was not that well understood. So he gives a different method to find out the rate of motion, because he was the first to, one of the first, not the first, one of the first to use the concept of derivative in finding the rate of motion of a planet. Longitude is there. What is this rate of change? Theta is the longitude, d theta by dt. So that involves finding the derivative of the sine function. So he had given that. But for planets it is more complicated, and one has to use, because some approximations will not be valid, and sine inverse, etc. comes. So he completely takes a different route. He says that this will not work. So I will use a different method. Okay. So there is no time, or it will be somewhat technical. So he gives a different method which is exact in his framework. In his framework it is exact. So he gives a method, and for the retrograde motion and so on. And Nilakanta Somyaji carried out a major revision of the traditional planetary model. According to him, planets moved in eccentric orbits around the sun, which itself moved around the earth. So it is some kind of a, let's say, quasi-heliocentric model in which all the planets are moving around the sun, and sun moves around the earth. So that is, he gets it from, he analyzes, how latitude is calculated, longitude is calculated and all that, and says that this is the way it should be done. This is the way the picture is. This is the picture, you see. And this is somewhat closer to, this is in 1500 CE. So this is essentially same as Tycho Brahe's model in 1582, around 1580. See, Copernicus had given the so-called heliocentric model in 1542, but it had some other defects also, because he was trying to follow Ptolemy too much, and those defects are not there in Nīlakanṭha's model. And of course, one thing is that Nīlakanṭha didn't say that sun is moving, earth is moving, he didn't say that. But he could say whatever was possible at that time, whatever is possible at that time from observations. So that is what he has done. So that is a definite advancement. Now, cosmological concepts. So this is a conference related to cosmology. So I'll just make some brief mention of that. See, for instance, in the section on kakshas in Graha Ganita of Siddhānta Shiromani, Bhaskara says, Tatra kakaksham tavadaha. There the circumference of the Akasha Kaksha is being told. He says, Khotigner Nakananda Shatka, etc., etc. Okay. So, scholars of astronomy say that the circumference of the Kaksha of Akasha is this big number, 187120, etc. yojanas. Some scholars say it is the circumference of the universe, whereas some ancient Purāṇikas say it is the circumference of the mountain, which goes by the name Adrishya Drishyaka. Those who perceive the celestial sphere as a fruit, which goes by the name gooseberry, amalaka, placed in the palm, say that it is the circumference of the Akasha in the form of the sphere, whose volume is filled by solar radiation, removing the darkness which was there inside. Okay. So this translation is by Venkateshwar Pai. He has done this thing. So it is of course written in beautiful Bhaskara's poetry. Karatala kalitamalaka vadamalam sakalam vidantiye golam. See, it's all nice. Okay. So this is he says this Akasha Kaksha is this one. You see. In fact, that is the, according to Bhaskara's conception, it is the distance travelled by each planet in a kalpa. In a kalpa, this is the number of yojanas which are travelled by each planet. Because according to the Indian conception, the linear velocities of the planets are the same. They will travel the same distance. Though because some are closer and some are near, the angular rate of motion, of course, will be widely different. So the same distance is, so this is what it is. He says then, in the Vasana Bhasha, he says, mathematicians describe the Kakaksha, which is the circumference of the Akasha, as equal to this many yojanas. There, how can the finiteness of the Akasha, which is infinite, can be told? With this doubt, this measure of the circumference of the Akasha, which is the Lord of the day and which is filled with brightness, is being told. That is why the ancient mathematicians say that it is the circumference of the universe. Some say it is the circumference of the mountain which goes by the name Loka. Since that it is our opinion, because of not having. Others say it doesn't mean that it is our opinion. Sorry, it doesn't mean that it is our opinion because of not having evidence. It is only possible to say that the whole universe is like a sphere on the palms. So you can't give the dimension and all that. It is not very, from this so-called Akasha Kaksha, it is not possible to say. So idanim swamatamaha. Now my personal opinion is being told. Brahmanda metat amitamastu nova kalpe grahaha kramati yojanani yavanti purvairiha tat pramanam proktam swakakshakyam idam matam naha. The universe may be or may not be bounded. You see, it's quite modern in his view. According to the modern cosmology also, but now whether it's bounded or not unbounded, I don't think it is completely clear. Professor Vahia may be able to say what are the exact these things, but I think there is still a lot of confusion. Whether universe is expanding forever and unlimited, or whether it is bounded. Our opinion is that the dimension of the circumference is no other than the distance covered by each planet in the Kalpa. What is stated by the earlier astronomers is the evidence. Our opinion is that this is known as its own orbit. So that is, he stops short of that. So But I think this has to be explored further. In what sense, these cosmologies are expounded in Puranas and how it is related to. Because you see, the astronomy texts themselves, they are tied down to calculations of the various things which are of importance, longitudes of planets, their positions, so then in the time, so then the eclipses and all that you see. So for that the cosmological models are not needed. Because what are mostly needed are angles, the angles are measured. So from that one can, various angles are relevant and you do the calculations. And they are complicated enough and you are, is focusing on that. So cosmology is not emphasized, but I don't know, there may be some text, I think Professor Srinivas may be able to throw some light on that. What do they say and how it is maybe related to these Puranas. So these need to be explored further. So I think with this I conclude my talk. I'm sorry, I hope it was somewhat not too technical, but I just wanted to give you a flare of how exactly this astronomy is practiced in India. Yeah.
Somewhere you say that trigonometry was not known to our in Puranas. Is that?
No, not Puranas. I'm saying Vedic times and all. At least, yeah.
So when do you think that trigonometry was used in Indian tradition?
See that for exact date cannot be told because this Siddhāntica has lot of trigonometry, and he would have referred to earlier these things, earlier trigonometry kind of a thing. So let's say and Aryabhatiya, the very full description is there, what is a sine, what is cosine, how to calculate that and all that, you see. So definitely from 499 CE and certainly maybe a few centuries earlier, definitely it would have been there. And it is in a particular form, jar tha, you see. Whereas Greeks were trying to find out the relation between chord and sine. Here it is the opposite, it is a modern trigonometry basically in India, except that they don't consider ratio, but the length, the opposite side length, that is called jiva, arja, for a particular radius. Yeah. So certainly I think our 3rd, 4th century CE trigonometry would be there, and I think Aryabhatiya summarizes that, what is known, and maybe gives more results.
Thank you.
Yeah.
What is the future that you see for the Indian astronomy?
I don't know. We have been seeing, what is there in Indian texts. We have been seeing, so they are full of, as I said, various calculations and details and various kinds of things which are certainly used for, Panchanga. And Panchangas can be definitely improved. I can say that straight away, I mean, nowadays it may be using traditional texts, you may not be getting accurate results. But that can be remedied very easily because some parameters have to change. And according to Indian tradition, there is nothing sacred about any parameter. They keep on changing. You see, what Grahalabhava does is different from what earlier texts did. You see, so for our practical purposes, Indian astronomy is quite sufficient for the day-to-day lives of ordinary people. But otherwise, I really don't know how it will be. Whether this concept will be used for some other more important developments, I really can't say at all.
So with modifications, etc., we will be able to get the eclipses, etc.
Yes, definitely. In fact, eclipses are already quite. Some of the eclipses are quite accurate. I have myself found.
But sometimes many people claim that they are erratic.
No, that's what. So if you take some, something like even, Surya Siddhanta, I don't think we have done it long back, 30 years back. Ram Subramaniam and myself had done it, the analysis. But I think probably we have to do it a little bit more, we have to do it more carefully. So with those parameters, it is not possible to get exact thing, But lunar eclipses mostly you can get, but solar eclipses you can't get from that. So for that you have to make some corrections. And with that correction, using the same algorithm, one can get accurate. I am confident of that.
Just to add to that, you see this coming lunar eclipse,
Yeah.
I was looking at the newspaper,
Yeah.
it says the complete lunar eclipse on 7th,
Yeah.
but we are celebrating on 8th according to Panchanga. This is the, I had this confusion and just wanted your comment on this.
No, that I don't know. I mean, in the instant of eclipse, where the sun and the earth shadow and moon are in the same time, that can be calculated. But why they are, celebrating? See, celebrating means actually observing it.
Observing.
See, that depends upon the. See, how do you define Purnima day and all that? So that depends what tithi is there at the sunrise. So because of that, there may be some this thing, Yeah.
For eclipses, I think it's purely observations. For
Purely observations.
Moksha, and
Yeah, Bacha Moksha and other, but how it is different, I don't know. Because some girl was doing the MPhil in our Madras University. So I started to calculate in 2018. So it was a complete, very, from Tantra Sangraha we did from Tantra Sangraha. So then it is, exact. About I think only a few minute difference was there.
Many panchangs we choose only the ephemeris data, so there should be no confusion on this.
But this time I was surprised because entire North India,
7th or 8th eclipse.
Everybody is holding only on the
8th, na? But in the newspaper it has come 7th November is the complete lunar eclipse.
No, the middle point of the eclipse as seen in India will be known, so
Okay.
there will be no confusion. There shouldn't be.
But
Yeah.
this is what.
That can be easy. In fact, it's quite.
Papers may have their own reasons for highlighting something. I mean, they might have picked up somebody's
Right.
some panchanga of somebody anyway.
And one more thing is that, one has to use a better text, like Tantra Sangraha, We found that Tantra Sangraha does the calculations, eclipse calculations better. But not many use the Tantra Sangraha text to do it, If you do that and he gives a good formula for the rate of motion of the moon, you see, he takes that. So all those things if you take into account, I'm sure that you will get the correct instant. With some small changes, definitely one can make,
Yeah, I just comments that there is actually a record of a 10th century AD prediction of eclipse in one of the Stonehenge treasures, where he does it precisely and he gets a lot of money from the king. So till 10th century AD it was used. The problem comes because of the precession of the earth, and they don't account for it properly. So Aryabhatta knows that there is a precession which I'm not getting correctly. So he says, please keep observing and changing the parameters. Some years ago we did some work where if you take Varaha Mira's formulation, it works for about 300-400 years around that time. You can accurately get the Rahu Ketu position and the eclipses. If you go beyond that, the precision adds error to that. And there's a simple correction that you need to make. It's a sine function that you need to add with that 27,000 year period that he gave. Then you would be able to use the same formulations to give more accurately. The only thing is that the ephemeris that now modern computers can allow you to do a much more parametric calculation. And the second thing is that for solar eclipse, defining exactly where it would be seen on the earth becomes very tricky because it's a very small piece. So lunar eclipses are predicted, like he said, routinely without any problem. You can fairly accurately define. Solar eclipses, where it will be seen is a difficulty that we have. But 10th century AD, there is a record of some priest having made money, been blessed by the king because he actually predicted the eclipse. The problem is in getting not the time and date of the eclipse, exactly where it would be seen. That requires a geometric transformation which modern computers do much more easily with much greater precision. But even modern ephemeris, if you look at many of these astronomy programs, they tell you that you don't use it beyond 3000 BC. So they are also accurate for 5000 years. Aryabhatta was accurate for about 500 years. And that is because of the precision of time.
Related questions. Do we have any account or description of just penumbral eclipses? Lunar eclipses, just penumbral.
Penumbral, no, I have not seen that,
Because we have in NASA records, if we see penumbral eclipses, but in our inscriptions, we don't see any eclipse. Even in our practice also, just penumbral eclipse, we are not observing.
Yeah. I have not seen that. I think Shailaja was mentioning something, there's one astronomer, I thought she was mentioning something about penumbral eclipse also. I'm not sure about that. But I have not seen it in text and all that, They will say how much is the eclipse, how much part of the eclipsed body is, how much it is eclipsed. What part of the eclipse
Any
body?
eclipse without umbral contact is not observed
Yeah,
in India.
yeah. That is not. I have not seen that being done. Yeah.
I want to make a remark on this penumbral eclipse. Parashara Tantra says, Sarva Bimba Dhuma Varanam. There is one kind of, among the 10 eclipses, it is mentioned. Later, people have omitted, and Brihad Samhita gives a different definition for Nirodha. Nirodha is one kind of lunar eclipse. Where the center is dark, then it is called Nirodha. For lunar, the center can never be dark as an eclipse. In the Brihad Samhita thing, but Parashara gives that definition. It is anyway minor clarification. I have one question for you.
Yeah.
On the formula you showed for the date.
Yeah. Let me take it from there.
Then my question is the following: if n equal to 0, it becomes 12.
Okay.
That means, did he have the concept of 0 at that time? Otherwise, he can't say that. As 0 as a number, generally it is believed only after common era it has come.
Formula is not given. Each day you add this much term from the winter solstice.
How many days have
The summer solstice, each day you add this much to the.
Yeah.
Correct.
That's all that's it.
Zero concept
Not written as a formula with a variable n.
No, that would mean then that formula may not be very, reasonable to interpret the.
No. He says very clearly, that from the winter, how many days have elapsed from the winter solstice. So then the duration of the day is very muhurta.
No, that is fine. That means even then, without the concept of 0, the first day can't come. No. The reason is this: in all other texts, the counting starts with 1.
Okay.
Whereas in the modern time, we start with 0. From what you said, it seems like that. That's why,
as he said, it's not written like that, but he's.
This can be looked into.
Yeah, but it is what he gets from the statement, we can write the formula. That's what I'm saying. And for other things also, other computation in nakṣatras and tithis and all that also.
about not history of mathematics as it is, but history of an idea of shunya or whatever. Shunya word is there, but the concept that it can even represent something like this. It's just a doubt and a question.
The arithmetic 0. Yeah, the arithmetic 0 is 3000 BC. So arithmetic 0 has been used, and this is used only in strictly arithmetical sense of the word.
Yeah.
You get the point. The sophisticated math, 0 for which India gets credited is 580. For when you actually have the rules of multiplying, dividing by 0, etc. Here he is using a simple concept of numerical, arithmetical 0. And that is as old as 3000 BC.
Okay, thank you, thank the audience. Patient hearing.
Thank you so much, Professor Shriramji, and I'm sure all of you will agree that he has been a great teacher, that at the end of the day, he kept you also engaged in the discussion and the participation was very good. Thank you so much, sir, for this. And thank you for bringing out, the significance of trigonometry for deeper understanding of astronomy. And with arithmetical framework, you also brought down some examples of formula for calculation of duration of time and relation between time and shadow, and particularly resolving perspective differences in relation to eclipses. So that has been a great contribution. There are a few important announcements. There is program happening at Shri Shri Radha Vrindavan Bihari Temple, which is main temple, as well as at Man Mandir simultaneously. Suppose this, you can participate in the program at the temple or Man Mandir. There is dinner arrangement at Govinda's Cafe, post this. And those who have not registered yet, please do meet our team, which will be standing just outside the hall. Please do it without fail. And tomorrow also, the program looks like this. In the morning, you have two options again. What we have written here is the farm tour from 6:15 a.m. onwards. And let me tell you, we have a lot of sustainability initiatives and other activities happening at the farm, which you would love to see. Something that we have done in relation to organic farming, the research experiments that we have done in relation to that, solar power plant that we have, rainwater harvesting pond of 9 crore liters capacity. That's a beautiful sight to go during the morning time. Also, however, you have an option to participate in yajna from 6 to 6:45 a.m. and post that, rest of the program goes on at Sri Sri Radha Vrindavan Bihari Temple. So with this, we come to end of the first day of the conference. And I would also like to thank the audience which has maintained with us online. So what a day. Thank you.